Hello everyone, I'm sorry I'm late today, so let's start. So we have to continue with exercise 8, right? And we need to prove, so let me see. So we have some relations here, R, Q, and Z. So these are some relations, and we have sets X and Y, right? And we have to prove, so this is A, we have to prove that the image of X union Y is equal to the image of, to the union of the image of X and the image of Y, right? But I believe that I did not write the definition of R here. So let me write first here some definition. So what's the image, right? So we have that R of X is the set of all elements B that are in the range, in the range of R, such that there exists A in X and A R B. So the ordered pair A and B belongs to R. Okay. So this is the definition of the image, right? We have X. So we have, for example, we have that R is some binary relation between A and B, right? And in this case, we take X is a subset of A, right? And then we need to find all the B, all the elements in the range of R, so in B, such that for them exists some element in X, and they form an order pair. Okay, so this is the definition of the image of X. And we have to prove here that if we have the union of sets, then the image is going to be the union of the image of each of these sets. Okay, and so let's prove it. And to prove this, all we need is just the definition, right? We need the definition. We need to use this union here somehow. So let me express that. So we have that B belongs to the image of X union Y, right? So by definition, this is equal to the set of B in the range of R, such that there exists A where A is in the union of X and Y, and we have A, R, B. Well, we have this order pair here. So this is this set here. So we have that for all B in this set is defined by this, okay? And this is true if and only if. So we can see that if there exists some A such that, well, A belongs to the union of X, Y, and A, R, B, right? So we have this. So we have that A is in the union of X and Y. What does it mean? Well, this is if and only if there exists A such that we have two options. Either A is in X or A is in Y. So either there exists A such that A is an element of X or A is an element of Y, right? And A, R, B. Okay. And from here, I think it's clear. So all we have to do, we have or here, but we have this end, so we have to distribute this end to this one and to this one, right? So we have that there exists some A such that A is in X, A in X, and A are B. Or A is in Y and A are B. Okay, so we have that exists A with this and with this. Okay, and then we can here if and only if this is true, all we have to do is to distribute this quantifier here to this sentence here and to this one. So if and only if, let me write that here, if and only if, so for the first case there exists A such that A is in X and A are B, and or, right, or there exists A such that A is in Y and A are B. We're almost done here. So we have this, and this really looks like this one here, right? All we change is just the set. So we have here that there exists A in some set and A are B. Well, this set in this case is X, in this case is the union, so it means that we can write this. So this is if and only if, write that here. We have that B is in the image of X, or B belongs to the image of Y, right? So this means that B belongs to the union, right? We have OR here, so to the union of this one and this one. So to the union of Rx union RY. That's it. So we prove that for all B in this set here, B is in this set as well, and then by definition these two sets are equal. Okay, that's it. This is the proof. Good. Now next we have B, 8B. We have AB, and so we have that X is a subset of Y. Okay, actually, if X is a subset of Y, then the image of X is a subset of the image of Y. Yes. So this actually is, so we can see that this is true, of course. I mean, if we have some Y here, right, and this is a subset of X here, right? No, X is a subset of Y, right? Then of course the image of X is going to be a subset of the image of Y, right? So we can see that from here, but still we have to prove. So we have, let's do it the following way. So we have the image of Y, okay, and since, look, we have that the wait. Yes. So we have the image of Y, and since x, so we can look, x is a subset of y. It means that the union of x and y is equal to y, right? Yes. So all we can do here is write just, instead of y, we write the union of x and y, the image of the union of x and y. Yes. And then we know from here, look, that this is true, right? This is the same that we have there. So we can write, the next step here is to write it like this one here. So this is equal to the union of the image of x and the image of y. So we have the union of two sets, and the union of two sets always contains these two sets, right? So if we have, for example, A union B, then we know that A is a subset of this, and for A union B, so B is a subset of this, right? We know this. So this set contains this one. So R of Y, right? Sorry, R of X. That's what we need here, right? So what did we obtain? We obtained that R of X. So we obtained that the image of X is a subset of the image of Y. And that's it. Okay. So, of course, we could have used the definition here again to prove this, but we don't need it, right? Because we can play with the properties that we already know. And what property we know here? We know this property, right? This thing here, we already found it here. So we don't need to use the definition and play with the elements of the sets. We only have to play with this one here. And that's it. Okay, so it's finished, this proof. Okay, next we have C. Let me write C over there. There's not. Okay, for C, we have to prove the following. We have to prove that the analog to this one, but not the union, but the intersection. Okay, so that R, the image of the intersection of two sets X and Y is not equal. Well, it's a subset of the image of X intersection the image of Y. So look, we have again, we did this the last class, and we had union and intersection, right? But we had composition in that case, right? Here we don't have composition, we have the image, but we can see that in the case when we have the union, and we come to this step here, to this step, no, to, sorry, yes, to this step here. This, for this, we have if and only if. Why? Because we have or, right? Since we have or, then we can't divide the, so we can apply this quantifier of existence to this sentence and to this one, and with if and only if. But if we have and, then we cannot apply if and only if. We can apply just some implication, okay? So because of this implication, we will not obtain that they are equal. We obtain that this is just a subset of this case. So this is not a subset of this. It means that they are not equal, okay? Good. So we have that proof. So B in the image of X intersection Y, okay? And again, we have to do just the same thing. So it means that there exists some A such that A is in the intersection of X and Y, right? And A are B, right? So and AB belongs to the binary, to the image of, well, belongs to the binary relation R. Okay, so we have this. Now again, this is true if and only if. This case, so A is in the intersection of X and Y. So A is in X and A is in Y, right? So we have that there exists some A such that A is in X and A belongs to Y as well, and A are B, right? Again, we can't distribute this, so we obtain if and only if there exists some A such that for the first case we have that A belongs to X and A are B, and so and A belongs to Y and A are B. Okay, now again, let me be very clear with this. Here we have and. So since we have the existence here, this quantifier of existence, this is, we can just apply, and so this implies that there exists this set and there exists this set. Okay, I mean that this holds and this holds. Okay, so this implies that there exists A such that A belongs to X and A are B, and there exists A such that A belongs to Y and A are B. Okay, and that's it. So we have now to rewrite this, but using so by definition, this means that we have that B, right, belongs to the image of X, and B belongs to the image of Y, right? So I have that B belongs to the image of X, and I have that B belongs to the image of Y. So this means that B belongs to the intersection of these two sets, right? So B belongs to the intersection of R X intersection of R Y. That's it. So we proved, look what we proved. We proved that for all B in this set implies that B belongs to this set. So that this set is a subset of this one. Okay, but not otherwise. Okay, so that's it. We prove this somehow. Okay, so this is C, it's checked, good. Now let's move to D. Let me erase this thing here. Oh, D. So I have to prove that the image of the empty set is the empty set. Well, that's clear if you think about it, of course. That's clear. The image of the empty set, of course, is empty because, yeah, but still. So all we have to do is the same that we do when we want to prove this kind of thing. We need to get that there exists some element that belongs to the empty set, and then this is false, and since this is false, then there's no element in this set. Okay, so it's empty. So let me write that. So we have that X belongs to this set. So let's assume that this is not true, right? Let's assume that that this is not true, that this is not an empty. So it means that there exists some X in this set here. There exists some X, okay? And then this is true, so by definition, let me write this is X that belongs to the range of R such that there exists Y and Y belongs to the empty set and Y are X. So by definition, if we have that this set is not empty, then there exists at least some X, and it means that we have this condition here. Okay. And this is true if and only if there exists some Y such that Y belongs to the empty set and Y are X. Okay, and what can we see here? We can see that if we say that Y is in the empty set, this is false, right? And since we're assuming that this is true, then all this is false. It means that, so this is false, right? So we get that this is false. So for all X, we have that X is not an element of R of the image of the empty set. It means that the empty set, the image of the empty set is empty. Okay, and that's it. Okay, nice. Now we have to continue with the number E. Let's continue there, over there. So here we have E, 8E. So we need to prove that the composition, so we have R composition Q, the image of this, okay, so the image of X under this binary relation here, that is a composition, should be equal to R, the image of R, the image of Q, X. So the image of Q, of Q under the relation R. Okay? Yes. So let's prove it. No question by me. Okay. So we have to do exactly the same that we're doing here, right? So we know that, so we want to prove that they're equal, then we will get some. So let's assume that B belongs to this set here, right? And by definition, this means that B belongs to the range of R composition Q such that there exists A and A, and yes, and A belongs A is A belongs to X. Yes, A belongs to X. We are talking about X, and this is what we change here. And A R composition Q B, right? So this is the same that we have here. For example, if we are talking here, so the set is X. In that case, is X, and all we have to do is to change this R, because we don't have R. We have R composition of Q, so we just write R composition of Q here. That's it. Okay, so A is in X and A R composition Q B. Now, what do we know? So this is true if and only if there exists some A such that A is a set, A is an element of X, and A R composition Q B. Now we have to look at this thing here, the definition of the composition. So again, when we have a composition of two binary relations, so AB belongs to R composition. So let me draw that here again. A B, right? And we have that here some R composition Q. Yes. So this is true if and only if, I mean, this is true if there exists some C here such that A Q C and C R B, right? Do not forget that the order is important here. So Q, the last one here, the one to the right goes first, and the one to the left go after that, okay? If you do it that way, so otherwise it will be wrong. So we have it. So by definition, this is true even only if there exists an A such that A belongs to X and what? And there exists there exists some C that we have AQC and CRB. Yes. Now, what do we need to do here? We can take this quantifier out, okay? And so we obtain that this is true if and only if there exists some C and there exists some A, right? And we have that that A belongs to X, and AQC and CRB. Okay, so this is R here. And since we have here and, we can't, and we know that it doesn't matter, right? If we have some, I don't know, A and B and C, right? Where A, B, and C are statements. So it's the same saying A and B and C, right? They are equivalent. So all we have to do here is just change this parenthesis here and write it here to these two things here. So let me erase this. So if and only if what? Yes, there exists some C and there exists A such that A is an element of X and AQC, right? AQC, that's what we need? Yes. And AQC and CRB. Now let's take this, since here we don't have A here, we can apply this quantifier just to this sentence here. So if this is true, if and only if there exists some C such that there exists some A and A belongs to X and AQC, right? And CRB. Yes, so it means that there exists some C such that, so we have, what is the meaning of this? There exists A such that A is in X and AQC. So C is an element of QX, right? Of the image of X under Q. Yes. And CRB. And now we have, if we look at this, so we can compare all this with all this. So this, we have that there exists some element. This element belongs to some set here. This is a set. So yes, this is the image of something, but this is a set, and this pair belongs to R. So so this is true if and only if B belongs to the image under R of what? Of this set, right? And the set of QX. Yes. So we prove that for all element in this set here, all element in this set here. So we have an element here if and only if this set belongs to this set. So let me write it anyway. R composition Q X is equal to R Q X. And we prove. So again, all we have to do here is just use the definition and play with the connectors here and play with the definitions inside it and the width. So it's not difficult at all. Okay. So let me continue. This was E, right? Okay. We finished with number 8. Now we are left with number 9. Let me do that over here. So number 9, the last one for classwork 4. We have that, suppose that R is a binary relation between A and B, sets A and B, for A and B non-empty. Okay. And then so the inverse of this relation is not equal to the complement of R. So again, we have some binary relation R between A and B, right? And all we know is that A and B are non-empty. And then we have to prove that these two sets are not equal. So we have to consider all the possible cases for R, right? So R can be empty, R can be non-empty, and maybe the intersection of A and B is empty, maybe it's not. Okay, so we have to consider all these cases. Okay, so let's assume that R minus 1 is equal to the complement of R. So we are going to get this by contradiction, right? R minus 1 is equal to the complement of R. And so we have 3 cases, like I told you before. So either we have that R is empty, right? Because R is just a subset of this, can be empty, of course. Or R is non-empty, but then we have the case for the intersection of A and B is empty, and when the intersection of A and B is non-empty. So this is the cases 1, 2, and 3. Okay, and that's right. 1, 2, and case 3. Okay, so we have to prove that in each of these cases we need to get some contradiction, of course, with this. Okay, so let's look at case number 1. So in this case we have that R is empty, right? So if R is empty, it means that R minus 1, the inverse. So do you remember? So if we have that AB belongs to R, then this is true if and only if BA belongs to R minus 1, right? So we just have to change the order. And if we have no element here, then of course we have no element here as well. So this is empty. But if R is empty, then the complement of R is going to be all these, right? So the Cartesian product between A and B. Okay? So we have that the complement of R is equal to the Cartesian product of A and B, right? And we know that we have A and B non-empty. So this Cartesian product is non-empty, right? So we obtain that r minus 1 is not equal to the complement of r. So we got the contradiction because we assume that they're equal, right? So for the first case, we already got that contradiction here. That's good. So look at this thing here. It is important for us that A and B are non-empty, right? Because if one of them is empty, then we get that this Cartesian product is empty as well, okay? And then this is not true. This will be not true. Okay, so now for case 2, we have that R is non-empty. And let's take that the intersection of A and B is empty. Okay. So it means that, let me continue there. So I have that R is non-empty and the intersection is empty. So it means that there exists what? There exists some element of R, right? There exists some order pair AB such that AB belongs to what? To the Cartesian product of A between A and B, yes, and AB is an element of R, right? So this is true because R is non-empty and the A and B is non-empty as well, okay? And R is a binary relation over from A to B, okay? So we have this, and so we have that A, so we have that A and B belongs to R. So this means we write this like A, R, B, right? But this is true if and only if B, R minus 1, A. So if BA, the order pair BA belongs to R minus 1, okay? And then since we assume that they are equal, that R minus 1 and the complement of R are equal, then we assume that, then we obtain that B are complement of A. So that that the order pair BA belongs to the complement of R, okay? And now, since the complement of R, so the complement of R is a subset of the Cartesian product AB, right? So R is a relation from A to B. It means that the complement is as well a relation from A to B. Then, so here, then, look, this B belongs to A and A belongs to B. So look, the complement of R is a subset of the Cartesian product AB, right? And we have that BA belongs to the complement of R. It means that B is a subset, is an element of A, and A is an element of B, right? So B is an element of A, and A is an element of B. But we know that A is an element, so that B is an element of B, and A is an element of A. So it means that the intersection of A and B is not empty, right? So the intersection of A and B is not empty, right? Because we have that, so we have that B belongs to A and B belongs to B as well. And A belongs to B and A belongs to A. Right? So elements A and B are in both A and B sets. So we have that the intersection is not empty. But we assume that the intersection is empty here. Right? So we obtain that this is a contradiction. So it means that for this case, we also have that this is not true. So we already proved for case 1, for case 2. Now we're left with case 3. Okay, I can see that. Wait. 1, 2, 3, 4, 5, 6, 7, 8. 8 plus U, so 9. So we have 9 students right now, but we have 22 in the course. So something is wrong. Okay, less of the half of the students are listening right now. That's not good. Please let me remind you that the deadline for homework 2 is December. So write that here. Deadline of homework 2 is December 30. Okay. And the last seminar is, I think the last seminar is on December 29. Okay, so we still have 2 more seminars. So today plus 2 more seminars, and that will be it for this semester. But we continue the next year. Okay, so I listened to yesterday that the lecturer said so we will have. So you will have a final grade from 1 to 10, right? So your final grade is from 1 to 10. I hope you understand how it works in this case. So that if 3, 4 is 3, 5, 6, and 7 is 4, and 8, 9, and 10 is 5. So excellent, good, and pass or something like that. Okay. So this is the grade system here, how it works. So there are 2 kinds of grades. So the one from 1 to 10 and the other from 1 to 5. Okay? And your grade will be taken from your homeworks and from a final test, I think, that you will have. So that depends on the lecturer. Okay, so do not forget about the deadline. I think, yes, we will have another homework, so homework 3, and the deadline for this homework, I think, will be January 16, 19 or something like that. Okay, yeah, that's it. Okay, so let's continue. So we are left with case 3. So in this case, we have that R is not empty, and the intersection is not empty. So we need to get some contradiction in this case as well. So it means that there exists. So since the intersection is non-empty, so there exists some A in the intersection, right? There exists some A in the intersection, and then the order pair AA belongs to R, right? Okay, such that, let me write AA is an element of the Cartesian product of AB, right? Because A belongs to A and A belongs to B, okay? So we have this. It means that we have two cases. Either this ordered pair belongs to R or it doesn't belong, right? So if AA, the ordered pair of AA is an element of R, then it means that AA is an element of R minus 1, right? We are changing the order here, it doesn't change. So we have that AA is R, it means that AA is in R minus 1. And we are assuming that this is equal to the complement of R. Okay, so since AA is in the complement of R, then it means that AA is not an element of R, because it's an element of the complement, and if it is an element of the complement, then it's not an element of the set itself, so of R, right? But we assume that this is an element of R, so we get the contradiction here, right? Now we have to assume that this is not an element of R. So what if AA is not an element from R? Then we have that AA. So since it's not an element of R, then it is an element of the complement of R. Yes, and we know that the complement of R is equal to R minus 1 because we assume that. And then it means that AA, if we change it, we obtain the same. AA is an element of R, right? Because AA is an element of R minus 1. Then it means that if we change the position, right, then AA, we obtain the same, is an element of R. But we assume that it's not an element of R. So we get the final contradiction here. Okay? And that's it. So we prove that for all cases, for case 1, case 2, and case 3, this is not true. We got some contradiction. It means that we prove it. Okay? So we finish with this proof here. Good. Okay. Good. Now we have 20 minutes to start with the new problem set. Problem set 2, right? Yeah. Which one was that? Let me check. Where is it? Where is it? It should be here. So the exercise 2 was make a finite sketch for the diagram of the relation on the set of the natural numbers. Okay. I see. Well, I forgot to ask about this one. So I mean, it's just I understand how to make this diagram, but maybe there's some special figure that we need here. So the next time I will not forget about it. Okay. So exercise 2. Remember me, please, next time from exercise 2. So let's start with problem set 5, right? Yes. Well, I think I'm just going to talk about, well, no, I think exercise 1, I have time to do it. So we need to talk about functions now. So we have been talking about, we started with sets, right? We define what a set is. Then in the set, we define order pairs. And then we define that there are some binary relations. So we define the Cartesian product of A and B. And then some subsets of this Cartesian product are called the binary relations from A to B. Okay. Now we need to look we need to look at some special kind of binary relations called functions. Okay. But before that, we need to look at 4 different kind of binary relations. Okay, with some properties. So so we have that. Okay, let me give me a second. So let me remind you that definition here. We have that R is a binary relation, right? R is a binary relation, and we call it. We have 4 different ways to call these binary relations. So it's functional. It can be either functional or injective or total or surjective, right? And the definition is the follow. So this is, so R is functional if for all x and for all y and for all z, we have that if we have x, r, y, and x, r, z, this means that y is equal to z, right? So it means that, look, for this case, if we have x, here x, and yes, so x, r, y, and x, r, z, right? So if we have, this is r and r. If we have this, and this is functional, then y and z should be equal. So this is not possible, right? And this is called functional. Okay. Now, injective, if we have again that for all x, y, and z, we have that if y are x and z are x, then y is equal to z. Okay, so in this case, we have here y are x, so this is x, this is y here, and z, sorry, yeah, so z is here, so no, y is here and z is here. So we have y are x and z are x. If this is injective, so this is not possible because this should be equal. So y and z should be equal. Okay. So if we see, right, so all we have to do here is change the domain, if I can say like that, yes, with the range. So it means that if r is functional, then r minus 1 is injective, right? And if r is injective, then r minus 1 is functional. You should have proved that or something. Okay, but this is quite clear. Now is total if, we call it total if for all x that, okay, sorry, I forgot to write here that it's not just total. It should be total for something. So it's total for example, Z, if for all the elements of Z, right? So all the elements in this set Z, there exists on Y such that X are Y. Okay, so in this case we have R, right? We have from some, I don't know, A, B, right? And then we take some subset of B, Z here. Yes, we have here some elements here. And then we look at all the arrows, you can say, all the binary, all the pairs, right? But within Z, okay? And then for each of the elements here should be exist some X. So if this is Y, no, sorry, this is X and this is Y. So for each of the elements X in Z should exist some Y such that Y are X, okay? What? Y are X? X are Y. So, well, no, I'm telling you in this direction, sorry. This is another definition for injective. Okay, yes. So if I have yes, so it's total for Z is for each of the elements of, so this is going to be A, this is going to be B. So we have that R is a binary relation from A to B, right? So from A to B. So for all X in Z, there should be exist some Y here such that X are Y. Okay, now it's correct. Okay, and surjective means that if for all Y in Z there exists some X such that X are Y. So, and this is what I was talking about actually. So if we have here A and B, then we look at some subset of B, we call it a Z, and then for all the Y in Z, there should be exist some X in A such that we have X are Y, okay? And this is surjective, I forgot, for Z as well, okay? So this is the four kinds of binary relations that we have: functional, injective, total, and surjective. And from this we can define what is a function, and we can define what is a bijective relation. Okay, so let's look at the exercise 1, and let's try to make some examples here. So exercise 1 is that we have to give an example of some, so this is class work 5, okay, 1A. So we need to find we need to give some example of a binary relation P in the natural numbers, so some P from the naturals to the naturals, such that we have that is functional, not injective, total, and surjective. Okay. So if we take, for example, two sets. Okay, so this is set A and B, right? And we need some binary relation P. We need it to be functional. So functional is that, so if we have, for example, 3 elements here, and let it be here 3 elements as well. So functional means that from each of these elements, we have only, so from each of these elements goes at most 1 arrow. Okay. So for example, this thing here, so this is functional. Okay, this is functional. It doesn't matter that we don't have this. So if we have this and we have arrows here, it means that it's functional and it's total. But we care about by now that it's functional. So this is functional. Good. Now don't forget, if we do something like this, so this is not functional anymore. Okay, so this is functional. Now we have not injective. So it means that to one element here we can have 2 arrows. Okay, so for example, we can have the following. Oh, sorry, no, of course. That from to this element we can have 2 arrows, so these 2, for example. Okay, so now it is still functional, and now it's not injective because we allow this, and now we need it to be total. So it means that we have to, from all the elements here, we need to draw some arrows. So let's draw it to this one. Okay, and surjective. So it means that for all the elements here in B should have some arrow. Okay, we have this without arrow. We can just do the following. We can just eliminate it, and that's it. So we have this P here is functional, not injective, total, and surjective. Here we have 3 elements. Here we have 2 elements. Okay, and now we have to think about something like this, but for when we have natural numbers. Well, it's not easy. Okay, I don't know, for all the natural numbers, let's take this one. So let P be the following relation of A, for example, A 0, such that A is a natural number. So what kind of, so if we draw this here, we have here 0, and we have here the natural numbers. So the natural numbers. So for each of them, from 0, 1, 2, 3, and so on, n, we have this. So again, this is functional, only 1 arrow. This is not injective because many arrows come from 0, all of them actually. Total, because for all the elements from here we have an arrow, and surjective because the only element here is 0 and we have an arrow for 0. So this works. This of course is not, well, it is, but we are taking here the naturals, and then we are taking here not all the naturals, but only the singleton of 0. Okay, so P in this case is a relation from the naturals to the singleton of 0. You can change this 0 for any constant, for any natural, okay, and it works. Okay, so I think this works for our case. Okay, now for B, so now for B we have that P must be the following. So P must be functional, injective, total, and not surjective. So if we have again here 3, we have here 3. So we need it to be functional. This is functional. We need it to be injective. By now it is injective. Now we need it to be total. So from all of them goes, we have an arrow. But since it is injective, then it can be go like this. So this is functional, injective, and total. And we are left with not surjective. It means that not all the elements from here should have some arrow. So all we have to do is just draw a new element. Okay? So there exists some element in here without arrow. Okay? And how are we going to define this P in this case then? Well, what about so let P be the following. All the pairs A, B that belong to the Cartesian product of the natural numbers such that B is equal to 2A. We can take 2A or 3 or 4 or 5, doesn't matter. Okay? And then we have the following. We have that look, for A, so for every natural number, this is defined. So we can take A equals 0, 1, 2, doesn't matter. It's defined. So we have here 0, 1, 2, and so on. Now, is injective? Yes, because if we have that B is 2A and C is equal to 2A, then it means that B is equal to C. It means that this is injective. Okay? And total, well, I already said about total, functional, this is the same. And not surjective. Why is not surjective? Because this here we have arrow only for even numbers. So B, so B is an even number, right? So it means that for all the odd numbers here, the odd numbers here doesn't have an arrow, because we cannot obtain the odd number if we multiply, if it's the product of 2 by something, right? So this means that this is not surjective, and this works. Okay, good. And for the final one, and I will finish with this one for today. This is C. Okay, let me. So this is C. We have that P is not functional. P is not injective. Not total. And surjective. Well, it means that we can have something like this. So again, not functional, so we can have this. This is not functional. Now, not injective, it means that we can have something like this. Yes, so not injective. Now, not total, so we have something missing here. So we have some element for which we did not draw any arrow. And surjective, well, this is surjective, so we need to draw something like this, okay? And I'm going to use the following. So let P be all the pairs such that A is greater than B. So P is equal to the relation of A being greater than B, okay? And we can prove that. So this is not total, so not total, because 0, so 0 is, so we 0 for any natural n, 0 is not greater than n, right? So we have here 0, for example. Good. Now, not functional, because if we have, for example, that we can have that 5 is greater than 3, and we can have that that 5 is greater than 2. So this is 5, for example, and this is 3 and 2. So this is not functional. And not injective, because, for example, for this one, we can have here 2 and we can have here 4. So that 5 is greater than 2 and 4 is greater than 2. So it's not injective. And finally, surjective, right? Well, because for any number, for any natural n, we can find some greater natural number. Okay, so for any natural number, there exists a greater one. And that's it. So this is all we needed. And we finish with exercise 1. We will continue next time. Thank you very much. Uh-huh.